Hello. In this last segment, we'll examine some additional oscillograms from actual case histories. These cases demonstrate how recordings can be used to assess the performance of major system equipment, such as circuit breakers, transformers, and generators. Let's begin with Case 4, a breaker restrike. By way of review, you know that when a circuit breaker opens to interrupt current, an arc is formed between the parting contacts. Normally, this arc is quickly extinguished by the dielectric in the interrupting chamber, which may be air, gas, oil, or vacuum. After the arc is extinguished, there is voltage buildup across the open contacts. If this voltage builds up too fast, or if there is a sudden surge of voltage, the dielectric strength of the breaker's insulation could be exceeded. When this happens, the arc is reestablished and current again flows. This dielectric breakdown is known as a restrike. It can cause serious damage to the breaker contacts, in addition to deterioration of the oil or gas dielectric. But how can this happen? Well, here's one way. A lightning strike to a phase conductor flashes over an insulator, causing a single line-to-ground fault. The breaker at the substation successfully clears the fault, but a very short time later, perhaps a few cycles, there is a second strike to the line. The resulting surge in voltage causes the open breaker contacts to restrike. But in only a few cycles, the ionized gases from the original fault have not had enough time to dissipate. So the original fault reestablishes itself. Usually, the fault current will go out at the next current zero after a half cycle. Here's a set of oscillogram traces showing an actual restrike on a 500 kV air blast circuit breaker. The initial fault was on B phase to ground, and it successfully cleared after 7 cycles. About 1 cycle later, lightning struck C phase conductor, causing the breaker to restrike. In this instance, the original B phase fault was not reestablished, but a different fault occurred on C phase. Thus, the lightning strike caused both a restrike and a fault. The C phase fault current was extinguished 1/2 cycle later. Notice that the fault on C phase was more than double the magnitude of the initial B phase fault. Well, so much for breaker restrikes. We've seen how oscillogram recordings can be quite useful in spotting this type of breaker performance. Now let's consider case number 5, generator instability. We've already mentioned that unlike a fault that is cleared in a few cycles, instability may last for several hundred cycles. This is on the order of several seconds. But like a fault, the effects of instability can be captured on an oscillograph for future analysis. As you know, instability can occur when the rotors on the synchronous machine speed up or slow down in response to some disturbance. The disturbance can be a fault, loss of a generator or line, or a load change. This acceleration and deceleration of the rotor causes natural oscillations on the system that usually die out in time. Consider, for example, the loss of a generator on this power system. This trace shows megawatt flow into the area. The inflow immediately increases to supply the loss. But before the remaining generators settle down to their increased megawatt outputs, you can clearly see some oscillations. Most oscillations like these are well damped and die out in a few seconds. However, sometimes the oscillations actually grow in magnitude with time. You will remember that we discussed this problem of instability in an earlier tape. When instability occurs, we will see oscillations not just in megawatt flow, but also in voltage, current, megabars, and system frequency. Oscillations in voltage and current show up as envelopes superimposed on the normal 50 or 60 hertz voltage or current. This example shows generator terminal voltage and stator current recorded on a conventional fault recorder in the power plant. In this case, the unit lost synchronism and began slipping poles after a major tie line was opened. The recording shows about 1 second of the disturbance. At this point, the generator trips offline. You can see that oscillogram recordings such as these are quite valuable to engineers and others concerned with investigating a disturbance. They provide us with documented evidence of the disturbance and allow us to determine if the protection has operated as planned. Let's now move on to our final case study, Case 6, Transformer Energization. Here, we'll show how an oscillogram analysis can help improve switching procedures for system dispatchers. We're considering 2 different switching procedures for energizing this 500 kV, 230 kV transformer. In the first procedure, breaker C is closed to energize the transformer, with breaker D at the remote terminal open. In the second procedure, breaker D is closed first before energizing the transformer with breaker C. The oscillograph has recorded voltages and currents on the line side of breaker B at the transformer substation. Here we show the traces for procedure 1 with breaker D open. This looks quite strange. Voltage VA on the A phase shows some distortion, also VC to a lesser extent. And this current IA must represent transformer magnetizing current. Your workbook explains why only one phase is affected. First, recognize that we have 150 miles of open 500 kV line. This means that the voltage at the very end of the line at breaker D will be quite high due to the capacitive line charging. That is, the Ferranti effect. This voltage was measured to be 567 kV. In fact, there is a voltage rise all along the length of the line. At the transformer substation, the voltage is also quite high, 560 kV. The moment breaker C closes, this high voltage is applied to the transformer, forcing it into saturation. This results in a very large magnetizing current flowing into the unloaded transformer. As you know, this magnetizing current is distorted and unbalanced. This causes distorted voltages at the transformer that may very well stress the transformer insulation enough to cause a failure. The second switching procedure shows the effect of closing breaker D before energizing the transformer. Now we have normal load current flowing along the line before the transformer is energized. Since there is no longer an open-ended line, voltage at the substation bus is about 10% lower than when breaker D was open. Now, when breaker C closes, there is still distorted magnetizing current flowing, but it is much smaller in magnitude. This is because the voltage impressed on the transformer is much lower. In fact, you cannot even see the magnetizing current on the oscillogram because it is very small and superimposed on the normal load current. But you can see that the transformer voltage is now much less distorted, so the insulation is less stressed. Our lesson here is quite simple. Transformers should not be energized from long, open-ended lines, especially high voltage lines. The proper switching procedure is procedure 2. Close breaker D before energizing the transformer. Okay, so we've now reached the end of our lesson on fault investigation and analysis. Our objective was not to make you an expert in interpreting oscillograms. Rather, we've given you a general overview of why fault investigation is important and how oscillograms and other tools can be used to understand and solve a variety of problems on the power system. Please switch off the videotape at this time and go through this material in your workbook.